screen?
Good day, yes.
Okay, we will start now. So, and we are working our mind with multi-component model of universe, and we discovered that dark energy, which we treat as a lambda term, start to be dominated 4 billion years ago, so 9 billion years, starting from the birth moment of the universe from Big Bang. Now we can estimate the age of the universe, as you remember before. So I can, let's write age of universe. As you remember, we just did it before in the beginning. Just take the Hubble constant and consider the value which is a inverse of the value of Hubble constant. But it is not right. It just give us the possibility to estimate very not precise the age of the universe, and we even could see that if we will not take into account the whole components of the universe, in this case the age of the universe will be really lower than, for example, the age of the some oldest object in the universe. So, and this is a problem. Now we will correct it, and we will find the age of the universe taking into account the components which we now have. And again, as we understand, so we are living now in the stage where much more important component, this is matter and lambda term. So matter plus, I will write dark matter, dark energy, which we consider as a lambda term. So again, the radiation is not so important, because we estimated that for now the radiation is not dominated anymore. It was sometimes before, and just quickly to remind that we can consider this 3 stage. So this is lambda, or let's write like a dark energy or lambda stage, here matter stage, and here radiation stage. So, and if we put here 0, here time, we are living something like here, okay, in this time. In any case, to be precise, so we can consider. I will write what for us will be important. So we can use the model of matter plus lambda term, and for this we obtained the expression relation between time, this one, between time and scale factor. So I will repeat it here. So this is 2 divided on 3 square root omega lambda logarithm a divided am lambda. This is what you need to obtain, plus 1 plus a divided on a m lambda cube. So for the present time, we use the notation T0, and this is exactly means the age of the universe. So A 0 equal 1. So we decided to use such a kind of notation, so I consider the expanding of the universe starting from present time. We also know that before we found that we can find the scale factor where here. Okay, so equal omega, I will repeat, m0 omega lambda 1 divided on 3. And in this case, if you want to find the age of the universe in this expression above, we need to put here 0, and here 0, which is equal, okay, 1. So, and to put instead of am lambda, because we would like to find the expression through the values which we can, parameters which we can observe. So in this case, we obtain T0. This is age of the universe. 2 divided on 3 H0 square root omega. We even can write it better because since we consider that k equals 0, it means that, and we consider also that omega r radiation approximately 0 for this time, so we consider this not dominated component of the universe. It means that 1 from the left side is omega 0 total equal omega m 0 plus omega lambda. So from this we can find omega lambda. I will write and to express everything through one parameter, which is a relative energy density of the matter. So it will be 1 minus omega m 0 logarithm. And here we will put, instead of 1 divide a m lambda, we will put this expression. So it will be 1 minus omega m 0 divide square root omega m 0 and plus this 1 plus m0 divide omega m0. Okay. We can, understandable, we can to simplify a little bit this expression. So it will be 1 minus omega m0 on logarithm. So we will have here square root 1 minus omega m0 plus 1 divide omega m0. So this is final expression to calculate, to estimate the age of the universe. If we will consider, so look, we before we put, we decided to use, okay, here 0.26, okay. So in principle, if we will put here our parameters, we can consider omega m0. Here we used, for example, which is you know, all time we can think what's better to use. Especially in the time when the space satellites give us a little bit different values, of course you can use new one. For now, we can use approximately 0.3, and to put it here, or for the Planck, it's 0.26 to be much more precise. Yes, I will write Planck. Planck telescope. So if we recalculate it to and we can see that this part, let's see, this one, which is depend on omega m0, became equal approximately 1.5. So this is just a number, which is, you know, 3 divided on 2, which is really, it looks like compensate with this approximately 2 divided on 3. So it's just, you know, such a miracle, because finally for this stage we obtain T0, the age of the universe, we obtain as 1 divided on H0. So because you remember, I was not so correct, because I would like to say that when we consider it the universe, single component of the universe for the just matter, in this case we obtain, if we will consider only matter, we obtained T0 as a 2 divided on 3, 1 divided H0. So which became less than the oldest age of the oldest object in universe, and this was one of the problem. Now you can see that if we will take into account only matter, okay, since the previous lectures. So now we can see that if we will take into account also dark energy, this dark energy, the T0 approximately, and if we will put all values, we will obtain the age of the universe, like approximately 13 and 8 or 7 billion years. So this is the age of our universe. So now you understand how to obtain it. This is this is some. So if we will speak about all objects in our universe, so they should be not older than the age of universe as a whole. Okay. Now I want to consider also the another stage, this one, the stage before we consider this one. So we will go a little bit in past, not a little bit, because radiation stage is really, we will estimate now the time. We will see that it was really far from this moment. So consider the model, or consider the stage and corresponding to the model. This is radiation plus matter. And also this important moment which correspond to the scale factor ARM, which we obtained before. Now we want to also to obtain TRM, when it was important moment, and this correspond to the situation when omega R equal omega M. So sometimes before we understand that it was a time when the energy density of radiation was dominated corresponding to the energy density of matter. So, and when it was, okay, we again can consider the Friedmann-Lemaitre equation for these two components of universe. And in this case, as you remember, we have in the left part the square of h divided on h0, and on the right side, if before we had, let's look here, we wrote a lot of things. For example, we can look on this equation. Okay, this one above, on this one. So this one, you can make a reference to this equation. So this is again related with a k, with a curvature, which we consider equal 0. And this is exactly omega, which correspond to total relative energy density of the universe. Okay, so if we will use this Friedmann-Lemaitre equation for these two stages, we can write that this is in the first radiation plus the matter. And if we will take into account again that h, this is a point divided on a, we obtain that it will be a point squared divided h0 square equal. Let's take out this multiplier, which is the same in two terms. And inside we will have 1 plus omega m0 divided on omega r0. Multiply on a. So now we can take into account that we found it before that the scale factor for this moment going from radiation stage to matter stage is omega r0 divided omega m0. Okay, so in this case we this is equal 1 divided on ARM. And finally, if we will remind that a point, this is dA by dt, we can immediately to write the relation between, for dt I will write for the time. So this is a dA divided on square root omega r0, because we need to take square root. And here 1 plus a divided on ARM divided on 2. So this is on the right side, we need to take integration. The right side, this is This is table integral, and you can find it. I don't want to. Okay, we can do it quickly. This is table integral a multiply on this square root, and we can write the right side. So this table integral give us 2 divide on 3, 1 divide on omega r0 square root we have. After this, we need to write ARM, and here I will write H0T, and I need to put from 0 to T for some time. Here I need to write a minus 2 IRM. This is what give a table integral. So this is nothing. Because this is integral of the so we can, it's integral like x 1 plus x divided on b minus 1 divided on 2 dx. So this is a table integral which can expressed exactly through the square root. And we need to put the limits, and limits we put from the birthday. It's better to say birth second, but even so from 0 to a. So finally we have that. Let me see. Finally we will have so h 0t equal yes, I will take out this 2, so it will be 2 divided on 3 AR square, because I will take out also the second ARM divide on omega R0. Here I will have 8 divide on 2 IRM minus 1. And here I will have 1 plus 8 divide on ARM. So like this. Again from 0 to a. So we need to substitute the when a equals 0 and when a equal a. So if you will do it, it's just a simple substitution. So finally we have what will be important for us. So we will have final expression that t equal 2 divide on 3 ARM square divide on H0 omega R0. And here, this is what give us 0, 1 minus so A divided on 2 ARM, 1 plus A divided on ARM. So like this. So this is final expression for the, which you know, final expression for the time through the expressed through the scale factor on the stage radiation plus matter. And for example, we can see that if we are on the if, for example, we are in the stage which correspond to radiation, so radiation stage, it means that the scale factor much less than the value ARM. Again, I will remind that if this is scale factor, so we speak about this is radiation, this is matter stage, and we are, for example, here. So if we will consider, we can, for this case, since we have A divided on ARM here, we can consider the series correspond to the small value of A divided on ARM, and instead of this, so we will have 1 minus, for this case, A divided on ARM square on the 4. So just consider the first terms of the series. If this is small, so this it's not convenient to write like this. Okay, in this case, we can for this consideration, we can immediately to write what will be T. It will be 4 divided on 3 RM square, and we will put here, so look, this will be 1 minus blah blah blah, and all of this we need to put in the parentheses with a 1 minus, so unities will disappear, and we will have only 1 divided on 4, 8 divided on ARM square. So in this case, disappeared this 4 and 4, and we can obtain, if we would like to calculate the time corresponding to the chosen scale factor, and we will use it for the inflation stage. We can immediately see that we need to put here approximately because we consider the series approximately equal. So 3 square root omega R0. I forget here H0. Okay. H0 multiply on T. 1 divided on 2. So this is the expression between which connect the scale factor and the time on the radiative stage. So when when radiation is much more powerful and have much more energy density than matter and dark energy. So, and we can see that for this A proportional T square root of T. So we can put it here that scale factor proportional like this. Otherwise, just a second. Well, if we have the situation when if we are in the matter stage, so it means here, let's put it matter stage. So for the matter stage, it means that And let's put it here that this is exactly the moment which we consider. So this is ARM, when we pass from one stage to another stage. You know, this is exactly, and the time which correspond to this moment, this is what we are using in cosmology now to discuss, because it's important to also to understand when the first structure appeared, how universe was born, and like this. So in this case, if A more than ARM, so we can see that this is of course more than unity. So, and we can forget about one in the front and multiply and to make just a simple simplification. So we will have, you can repeat it at home. You will have finally that H0T approximately we can consider as a 2 divided on 3 ARM square omega R0, and from all this this part for this Napolitans incredible. We will have only A divided on ARM like this. So this is a relation which we directly obtained from Friedmann-Lemaitre equation for this case. Again, we remember that all of this we consider for k equals 0. For k equals 0. In this case, we can see that A proportional T 2 divided on 3. So we can here to put T 2 divided on 3. So you can see that the universe, when in the space and universe, when we pass from one stage to another, start to evolve with the different laws. For example, if we remind here dark energy, which correspond to the present time, we are living in dark energy era now. So in this case, the space evolve proportional to exponent. So, and it means in principle that we obtained it before. Just let's look on this one. You see, so square root omega lambda H0T. Okay, I don't have possibility to write here. Okay, so it means that our future of the future of the universe, all time we would like to know the future. It means that the space will expand exponentially in the future too, and finally, as we suggest, and we can see from solution, if lambda, if dark energy, this is lambda term, all object will, not only all object, everything will be stretched, so the space will be stretched, and in the far future, maybe no any object will exist, because you know, it will be stretched such a way that finally even atoms will stretch also, and we will not have any connections. So this is the point. For now, we understand that it should be like this. But for now, I want to say that don't be scared. So it's enough things with which we can be scared, because it will be really far from this time. So we have enough time for our civilizations, not only our civilization but others too, to survive during billions of years. when the domination of dark energy will become really remarkable to influence on the distribution of matter. So now we speak about the radiation age, and let's find the time when it was. So it means that TRM, again we put this question. So we will use this expression, and so we need to use this expression for the case when, so let's put it here, for the case when A equal ARM. We exactly want to find the corresponding TRM. Okay, so we immediately can write that in this case, H0 TRM equal what we have here, 4 divided on 3, okay, ARM square, divide square root omega R0, and in parentheses we will have what we will have 1 divide minus 1 divided on 2 and 2 square root. Okay, let's put it here. So we will have if to simplify, we will have 1 minus 1 divided on square root 2 H0, of course we need to write here. So this is an expression which allow us to find the moment of time when we pass from the radiation stage to stage where matter dominates. So and if you can see also that again we can write it through the omega because we know that RM equal omega R0 omega M0. So we can in this case write that we can calculate, for example, 4 divided on 3 and this number, so TRM, which will be approximately 0.4, and instead of IRM we will put omega R0 omega M0. So finally we will have omega R0 3 divided on 2 divided on omega M0 square 1 divided on H0. So again we can put it. And so you can see that to obtain the time of the passing from the radiation stage to matter stage, it's enough to know omega R0, omega M0, and H0. And this is also a miracle because it's enough to know the parameters for the present time to find the time for the past. So it's really such a beauty of this expression of these equations. And if we will put, we know what is omega R0, omega M0, H0. If we will put these values, so you can check it, we will obtain approximately I can 100,000 years. So it means that when universe was so young, okay, like this, so with the age 100,000 years, which is a small age, as you understand. So this in this time, the universe passed from radiation stage to matter stage. So from this time, if T was much less than TRM, radiation dominates. And as soon as T became more than TRM, started to dominate matter. And we can tell that starting from this time, we can speak about beginning of formation of the structures in universe. This is beginning of formation of gravitating, we can say gravitating objects. So okay, we can not immediately because it should be also to pass some time, and in this stage, in the radiation stage, so you can put here remarks. The universe was in thermodynamical equilibrium. So it was a hot this stage, and the idea of the I hope we will have a time for this to speak, and the idea that and we start to speak already on the next lectures, that in the beginning of the history of the universe was very hot, and due to the fact the expanding of the space, the temperature decreased, and as a result, all time due to decreasing of the temperature, any next processes or switch on, sorry, such a way that correspond to some physical processes. For example, in a radiation stage that was a thermodynamical equilibrium, so it couldn't be period the gravitational connected bodies because the radiation was so high, with high energy, that it's prevent to create some gravitational connected object. But as soon as the temperature falling down, corresponding to this time and corresponding to the fact that the thermodynamical equilibrium was broken, so thermodynamical equilibrium, we understand that this is a number of ionization processes equal number of recombination process. So starting from this time, the emission, the radiation became free, and as a result, it stopped to connect with the matter, and matter start to behave, to evolve corresponding to gravity. And this time exactly corresponds of what is also very important, correspond, I will put here the arrow, the appearing of cosmic microwave background. So if we will speak, and we already spoke not once about cosmic microwave background, this cosmic microwave background appeared on the time TRM, approximately TRM. It means that investigation of CMB, when we investigate the cosmic microwave background, we investigate of the condition in the universe which were really in the incredible past, 100,000 years from the birthday of the universe. So we even can say that maybe this is the really ultimate past, which we can, in principle, look in the nature. Because to look even deeply, it's already complicated. So, but it's amazing that we now, our civilization, we are on such a kind of stage when we can construct the telescopes, construct the instruments which can look inside of the past of universe, which is incredible, which is 13 billion years far. So we can look and we can understand what's happened on the time when any structures didn't exist from the point of stars or galaxies. So the universe was very hot. We will look how hot it was. This is what I wanted to say. And if you don't, okay, we can, as a, you know, as a summary to put some sketch. So I can put it more beautiful, like this and like this. Okay, so let's put here, for example, oops, wait, okay, logarithm of t, and here logarithm of a for all stage of universe. So let's put here the moment of time t rm. So, and it was on the scale factor approximately, okay, we can 10 minus 4. I put here logarithm a, okay, logarithm should be minus, approximately minus 4. So, and we can write here that a proportional square root of t. And this is, I even tried to put corresponding to the how called the moment of time. So, and this is radiation stage. After this, we have the stage to Tm lambda. Not so beautiful because I will not have space for the next stage, okay, but you can do it better. So this is matter stage. And like this, I will put it much more steep. So a proportional, I will write through the lambda, okay? Maybe C should be here. Lambda T C. Yes, like this. So, and this is dark energy stage. And again, I already spoke about this. So the T0, this is here. T0, the present time. So you can see that we really, you know, and this on the stage when by fortune the dark energy started to be here, but not, for example, here, because if dark energy could start to be predominant, to be important on this time, So in this case, again, we can speak that in this case, no any structures, gravitating structures could be exist because they could prevent the gravitational contraction of the matter. So this is the point. If you don't have equation for this part, for the multi-component model of universe, we will start to discuss the problem of Friedmann-Lemaitre cosmology to prepare it to investigate the inflation stage of the universe. This is early time of, so we'll discuss how universe would appear. We'll have some questions. No any question? Are you here?
Yeah, we're here.
You are not surprised that we are living in the dark energy age and time. You're not scared that the universe will expand with acceleration in the future. Everything is okay.
Everything is okay.
Okay. Because sometimes students are upset with this conclusion. So, but don't worry, you know, as before, you know, we are scared that much more that the resources will be finished on the earth sooner or later, even soon. So, and we will have a problem even during the nearest 200 years, maybe even 100 years. So, and maybe as a result, we have a, you know, wars now between countries, because this is one also of the really problem. So, and we need to think in advance to use asteroids, to use another planets, moon, and like this. And God knows, maybe in the future we will change our universe on another one. So, because if we will reach the end, if we will finally consider the inflation stage, you will see the conception, the recent conception of the multi-universe. So, and maybe it can be some information, but it's strange to suggest that you things which looks sometimes fantastic. Okay, now we will jump, not immediately, but to prepare to jump really in the early age of the universe. So, and I promise you at the last 1 or 2 lectures to show you beautiful pictures, you know, to give you some presentation with the pictures of the structure and like this. But you know, to understand deeply, we need for now to write some formula. So the title of the lecture, okay, conclusion, I hope you wrote here. Okay, so the title of the lecture, problems of Friedmann-Lemaitre, it's called cosmology. So you could see that everything is good, and so we have 20 minutes, yes? 20 minutes.
Yes.
The problems that there are many problems in Friedmann-Lemaitre cosmology. Totally, and it was considered. It started to consider this that really this consideration has some problems in 1980s, and of course we have many questions to. And the first, we understand that we are all time using idealized models because we are human beings, and the structure of our investigations and theoretical investigation. So we start from more simple theory or more simple consideration, and after this we put much more component to consider what it is. So in principle, we can suspect that there can be some problems, and sometimes we solve these problems due to adding something else. But in Friedmann-Lemaitre cosmology, it looked like really fundamental problems. Of course, one of the problem, and together it's like 12 problems. But there are much more famous and fundamental problems. Is we say it's enough. Already have 3 of them, and we need to think what to do. The first, one of the problems, this is the birth of universe, because when we speak about scale factor equals 0, we put a equals 0. But it means that we consider this called cosmological singularity. So it means singularity. But there is a problem. Okay, but we used Einstein equation, which is a gravitational equation. Okay, equation of gravity, and we understand that we can't use this equation up to a very small scale, incredibly small scale, which correspond to the Planck scale. So when we consider the scale corresponding to quantum mechanics, where we need to switch on quantum mechanics, in this case we need to consider quantum gravity, which is not which we don't have yet, the quantum gravity such a way that describe all of this. So this is a problem, because in this case we even don't have a permission to of course we can use principle, and we will use now, since we don't have anything another, so we will use now the equation for the radiation age when we will speak about the early stage of the universe in principle. But considering that we a little bit around the Planck scale. But in any case, this cosmological singularity, this is something. So we can't say that the universe appeared from the singularity, from the 0. This is the first question. The second question, this is the question, but why k? Sorry, I didn't consider the case of the universe with a different curvature value, but I don't have just the time. So just to tell you that if k doesn't equal 0, so in any case, for the lambda dominate universe, in any case, in future will be exponential change. Yeah, I forget. Maybe later, if we will need, we will consider it. So for now, problems. Okay. The observational data give us that k equals 0. So omega 0 equal 1 plus minus. I don't remember exactly the last this Planck value of the errors of the unity, but let's consider W map. I remember it will be 0.02. So you can find it, look on internet. And And as you remember, if omega 0, the total energy density equal unity, it means that the space is a flat. But of course, there is a question, but why this is like this? So, and we will see, if we will have time now, we can start, that to provide this value equal unity for now, it should be incredibly precise in the past. This is so-called English. So it's a very famous flatness problem. Flatness problem. Flatness problem. So the flatness problem, let's formulate the flatness problem, but in the first we need to see if for now omega equal omega 0 equal 1. With accuracy, with this accuracy, with which accuracy it should be in the past. So to do this, look, we can use the equation which we obtained before. I will not show you, so you can find. So the before we obtained such a kind of equation. Again, it was from the Friedmann-Lemaitre equation. So h0 square 1 minus omega 0, h square is a function of t, a square on t. So see as the previous lectures. And the second one, we also, when we would like to look in the past, we understand that we need to take into account the matter and the radiation. So it means that even maybe better only radiation, but God knows, so let's keep the second one. For this, we have again our Friedmann-Lemaitre equation. And if we will put it h square here, we can finally will have the expression which will be for us useful. So this is 1 minus omega 0 a square divide omega r0 plus a omega m0. So we will use it now to estimate what was in the past. So look, if we have, for example, I want to see how it was on the moment of time TRM. So this is exactly when we pass from the radiation stage to matter stage. In this case, I can write that it will be, I will put the model, so it's understandable that, for example, if we agree with this one, this is from observation, okay? So the model 1 minus omega 0, this is approximately 10 minus 2. Okay, if we will look 1 minus omega, and I will put here index Rm because we understand that relative density, energy density change due to the time. So we will have 1 minus omega 0. Here we need to put Rm square divide omega r0 plus ARM omega m0. Okay, and we know which is the scale, this scale factor ARM This is approximately, okay, let's look. Huh? Here. Okay, here. 3 on 10 minus 4. Okay, I can 10 minus 3. Why minus 4? Yes, right. Okay. So this is 1 divided on 3000. So if we will put all of this, okay, here, we will obtain that it will be 10 minus approximately minus 5. Because omega 1 minus omega 0, we can put here module. This is 10 minus 2, okay, and we can put everything, we know, all values. It means that if we want to have, for example, we want to have this, the flat universe for now, for the present time, on the time of TRM, so it's a 100 TRM, remember this, 100,000 years. The omega 0 should be unity with the accuracy 10 minus 5. A little bit change, so and universe will be not a flat. The space will be not a flat. Okay, let's consider much more how sharp, much more limiting case, and let's consider Planck scale. Scales. So, and the point in principle, when we want to avoid the singularity, the cosmological singularity, we need to consider the Planck scale. So we say that, look, we around the Planck scale, we can use the Friedmann equation, but not less than Planck scale. So this is the idea. Let's consider the Planck scales, and you remember that we obtained this in the beginning, in the first lecture, that the Planck time. Oh, just a second. The Planck scale is approximately 5, 10 minus 44 seconds. So this is really, and we obtain the Planck scale from the fundamental constant. So, and we can consider this time as the ultimate time for the birth of the universe. So we can't say anything which is less of this time, but this is, if we speak about if we consider, sorry, I need to check this Planck scale, and we will calculate the corresponding scale factor. Okay, we will use what we have. We will use the expression for the scale factor for the radiation stage. So we just obtain it. I will use it. Divide on to this one. Okay, so we will use this one. Okay, 3 omega r0 h0t square root. And if we want to calculate for the Planck scale, we need to put here a Planck. So we have everything, omega r0, h0, t Planck, this is the time, the Planck time. If you will put it, so you will obtain approximately 10 minus 32. It means that the space contract from the present time and this value. And we can estimate that the module of 1 omega Planck, which we use here formula, okay, 1 minus omega 0, 1 minus omega 0, let's put module. And this is, of course, radiation stage, so it's not important to use the second summand. We can forget about this. Again, we will put approximately omega r0 a Planck square, yes, square. So if you will put all of this, approximately, we again know everything, approximately you will obtain 10 minus 60 or minus 61, doesn't matter. So, and this is incredible. It means that if to provide, we can write to provide for the present time, omega 0 equal 1 with accuracy 0.01, for example. Comma, it should be, okay, it should be omega, it should be omega equal 1 plus minus 0.000, and you write 60 zeros, 60 digits for the Planck time. Okay, time, let's write like this. So it means that if you a little bit on the Planck time, a little bit, the omega was different from unit, a little bit, it means to 60 digits. So the universe will be not a flat now. And this is exactly what we call flatness problem. This is flatness problem. Flatness problem. So, and I just want to say that it was discovered, this problem, that it was in, I don't remember exactly, like 1980s years, like this. And of course, the church, religion, people in church, they were happy because they said, look, this is exactly the proof of the God existence. because, you know, only God could make like this, to, you know, to put everything, all the parameters such a way that universe finally will become flat. The space universe will become flat, because it really looks like, you know, that something intelligent put such a kind of condition, the initial condition here, especially to make the flat, the universe is a flat principle in the future. Of course, we are scientists. Of course, we can believe in God like this. So this is our personal position and our personal consideration and personal opinion. But when we start to work in the science and the physics, for now, we try to exclude the existence of the God, because this is very simple solution of the problem. And we try to find the solution of the problem without involving of the God in our theory. Otherwise, it will be very simple why it's like this, but because this is wishes of the gods, or God, one God like this. So, and this is a point which should be solved, this is a problem which should be solved to explain why this is like this, and why universe is finally the flat, and why there is such a special condition in the beginning, especially when we will speak, and since we speak about Planck time and Planck scale, we understand that the space on this in this condition is really complicated, because it should be curved in the small scales. So as a theory tell us, and it's strange to suspect that when you grow up, when this universe grow up from the Planck scale, where really on the scale the curvature is not homogeneous, and finally the universe became homogeneous and then flat. So we need to find the explanation of this. And on this point, I will finish lecture. And on Monday, if everything will be fine, so we will consider also the two problems of the Friedman cosmology, and start to speak, and we will start to solve this problem, considering we will consider the inflation stage of the universe. So, do you have some questions?
Олена Юрівна, будь ласка, at the last lecture we had home task. Tell me please, what needs to be found? For example, I'm sorry.
Okay, so the idea.
A function t, what found?
You need to find this. Look, I will put here this expression.
H0t?
Yes, H0t, which expressed through A. Exactly this expression.
Okay.
From this one.
Okay.
Or even from this one, you know, we put it here. Yes.
Okay. Could you give us question for the exam?
Okay, I will prepare it, and also we will speak later, or maybe on next lectures, about how to provide everything, because as university said us that we need to now to use Moodle, and it's really annoying to use Moodle. So, and maybe I will ask you finally to resend what you send to me. I will check, of course, all what you send me, but to resend it in Moodle, I will look on this. I didn't work with Moodle before, because it should be everything posted in the Moodle system, that university will control what you did during semester like this. Yes, I will prepare, but I think you can find the question of the course on the page of astronomy department. So, but okay, I will send you on Monday like this. Okay.
So, thank you very much.
In principle, I can tell that all questions will be related only to the lecture course. So I will try to avoid the possibility to give you some question, but maybe I will give something for home task, but principle, everything I will orient on the lectures. Okay, other questions? Okay, no, wait. I didn't make okay. Screenshot. But can you tell me, as I could see, there are many students on your course, like 40 or 35, but I all time can see only 12. This is your normal presence on the lectures?
Yes.
Or sometimes you have 25, 30, or no?
I don't think so.
60, 50 maximum.
How maximum? 15?
15, yes.
Yes.
Okay. Okay, thank you very much for today. So we will see you on Monday, and good weekends.